Astute observers may recognize that I am not, in fact, Jared Lander. I'm Max Kuhn, and I'm here to introduce him. So Jared is the Chief Data Scientist at Lander Analytics. He's also the organizer of the New York Open Statistical Programming Meetup and also the organizer of New York R and DCR conferences. He's an adjunct professor at Columbia, and that's where he got his degree in statistics. He's also the author of R for Everyone. And he's going to give a talk on comparing tree-based models. So welcome, Jared.
A couple of years ago at the DC conference, I gave a talk about many ways to fit lasso regressions. So now we turn our attention to decision trees. There are so many types of trees, and we're going to talk about a lot of them. We will go over a little bit of math. We'll see how to train the models, compare their speed, check their accuracy, visualize the trees, and see a unified interface for all of them. First, the data. This is credit data. It has a binary outcome variable. Because 90% of the time when people talk about ML, they think of binary classification. Decision trees can also do numeric outcome variables, Poisson variables for count data, survival models, multi-class classification, and other types. But we are going to focus on binary outcomes today. And the inputs can be either numeric or qualitative. This dataset is imbalanced, and it would be better for classification if it were balanced. So we go to the recipes and themis packages to upsample the data. We are also going to make sure that the categorical variables are not factors, because strings as factors equals true is the default for this package, like we've learned nothing from base R. So now the data are balanced. We will look at single trees to begin. In this simplified case, we have two numeric inputs and a binary outcome. And the idea is that we want to break up this data space into homogeneous regions, or at least as homogeneous as they can get. We want any one region to be as uniform as possible. Then, when you get a new data point, you find which region that data point begins in, and then for the two-class classification problem, you take majority rules. So it's the percentage of the largest majority becomes the prediction. This generalizes to the multi-class case. If it's a regression problem, you still break the data space up into regions, you get a new data point, you find which region it belongs to, then the prediction is the average of that region. rpart was one of the first packages for fitting decision trees, and it stands for recursive partitioning, because you are continuously breaking up the data space. This can fit regression models, classification, Poisson, and survival models. Now it only has a formula interface. Categorical inputs can be either characters or factors, and a categorical outcome can be character or factor as well, and this handles missing data for us. You call the model with outcome tilde inputs. And in this case, the dot stands for all the other variables are the inputs. You can plot this with rpart.plot. And this is where we can see it gets the name decision tree, because as you ask a series of questions, it creates a branching pattern. It's very easy to understand for simple trees. A nice thing about trees is that variables get used repeatedly, so you can make a variable importance plot. In this case, it is the sum of the goodness of split for each time the variable was used. There are a few tuning parameters. Perhaps the most important is max depth, the maximum number of splits for terminal nodes. It's how deep and complex a tree can get. But why fit one tree when you can fit hundreds of trees? Leo Breiman and Adele Cutler came up with the idea to take B bootstrap samples of the data and fitting an independent tree to each sample. This is bootstrap aggregating, or bagging. So that's the first level of randomness, repeatedly sampling the data. But there's another level. When you're fitting a decision tree, you have to decide where to split the data, and you would consider all the variables. In a random forest, each time you would split each tree, you randomly sample the columns that you'll consider, and then judge those which one should be the splitting column. So there are two levels of randomness. The randomForest package is aptly named and is a wrapper around Leo Breiman's Fortran code. This can do both regression and classification, and it has a formula interface and an XY interface. If you're using the formula interface, you have to be careful that categorical variables are stored as factors. If you're using the XY interface, the input matrix must be dense, and this does not handle missing data. So we go back to recipes, and we do KNN imputation on any missing data, and we make sure that all of our categorical variables are factors. We fit the model using the formula, and it might look like just another formula, but we had to be careful that categorical variables were stored as factors. If you plot the model, it shows you the error rate as a function of the number of trees. We can see that there is a quick drop-off, but it very quickly after that levels off and doesn't improve much by adding more trees. The variable importance is how much each variable contributes to increases in accuracy. Now, random forests aren't supposed to need tuning, yet here we are. There are a number of tuning parameters. Perhaps the most important are ntree, the number of trees to grow, and sample size, how large of a sample to draw for each round. Ranger, sort of like a forest ranger, is an alternative to random forest written in C++. This can do regression, classification, and survival models. And in the formula interface, categorical inputs can be either character or factor, but a categorical outcome must be a factor. If you use the XY interface, you could use either dense or sparse matrices. And another nice interface is you can provide a data frame, then tell it the column that stands for the outcome variable. This also does not handle missing data. So we use the same imputed data frame we used earlier, and we call ranger using the formula. And in order to get a variable importance plot later, we set importance equals impurity. Calling plot on ranger returns an error because there's no plot method defined for it. So this is an expected error. Luckily, we can still get a variable importance plot, and this is how much each variable contributes to increases in accuracy. There are a number of tuning parameters, including numTrees and max depth like we've seen before, and also regularization factors as a way of penalizing the model for overcomplication. But instead of fitting individual trees, we can stack the trees by boosting. Now, boosting works with any type of machine learning, but it's mostly done on trees. The idea is that you fit a model, and then the next model uses the first model's residuals as the outcome variable. And each subsequent model uses the prior model's residuals as the outcome. This allows the tree to get smarter and smarter each time it's fit. The idea is that you stack a bunch of weak learners, like a bunch of stumpy trees. GBM is the original gradient boosted machine. It can do regression, classification, Poisson, survival, and ranking. Now, it mostly has a formula interface. It's possible to use XY using a different function, though. Categorical inputs must be a factor, and a binary outcome variable must be 0, 1. And it does handle missing data for us. So we use a recipe to make sure that status is 0, 1, and that all of our other categoricals are factors. We then fit the model using a formula, and we explicitly say that distribution equals Bernoulli. And we say nTrees equals 100 to do 100 rounds of boosting. When you call plot on this, it creates a partial dependency plot. Now, this one might be a little ambitious, trying to show 3 variables at once, but it's nice that we can. And of course, you could show fewer variables. The variable importance is the relative influence of a variable in reducing loss. Here's the tuning parameters, with nTrees being the number of boosting rounds probably being the most important. Interaction depth controls complexity. It's how deep a tree can go. And shrinkage, it's the learning rate. C5 is a nice alternative for boosting. And it can also fit a single tree if you want to. All of these can. Now, C5 only does classification. If you're using the formula interface, the categorical inputs can be either character or factor, but if it is a outcome variable being in classification, which it has to be, it must be a factor. It also has an XY interface where you could use dense matrices, and this handles missing data for us and generates rule-based models. So here, we convert status into a factor inline in the formula, taking advantage of that property of formulas. And we say trials equals 100 for the number of boosting rounds. When you plot it, you can choose which subtree to start plotting at. And this actually gives us a pretty complicated tree. Whenever you get to boosting, it gets very hard to understand your trees. Also, the variable importance plot, when you're boosting with C5, it's showing you the percentage of training samples found in terminal nodes after the split, but it's not really giving us much information since they're all at 100. The main tuning parameter is trials for the number of boosting rounds. Next, we get to the master of Kaggle, xgboost. This can do regression, classification, and ranking. Now, it only takes the XY interface, but you have to feed it into the special xgb.d matrix object. The X matrix can be either dense or sparse, or even files on disk. For binary classification, the outcome variable must be 0 or 1. This handles missing values for us. It could even handle imbalanced data for us. And it can also fit GLMs, which is pretty cool. You can fit a penalized linear regression. And it can be trained on either a CPU or a GPU. We use recipes to make sure that our outcome variable is 0, 1, and we convert all the other categorical variables into dummies. We create our sparse matrix for X and our dense matrix for Y, and we put it into this xgb.d matrix object. Notice the notation, they're calling the input data and the output label as if regression was an afterthought. Then we train the model with xgb.train. They're using this xgb notation because they're trying to emulate a Python environment. So we call xgb.train, give it the data. We tell it the objective is a binary logistic. We're doing 100 rounds of boosting, and we're printing out the error rate every 10 rounds. While there is no plotting function, we can plot using digraphs the error rate as a function of the number of trees, and we can see it gets better and better and better. And since we're not using a validation set, we have to hope it won't overfit. You can use xgb plot multi-trees to try to plot all of the trees into one display. I don't recommend this because this isn't that useful even for a single tree. Variable importance is the fractional contribution of each feature to the model based on the total gain of that feature splits. There are a lot of tuning parameters for xgboost, and you're pretty much just going to brute force your way through these tuning parameters. The most important are n rounds for the number of boosting rounds, eta for the learning rate, max depth for how complicated each tree can get. But you can also combine subsample, call sample by tree, and num parallel trees to create a boosted pseudo random forest, which is pretty cool. An alternative to xgboost is LightGBM. Now, it's not on CRAN yet, but the package authors, I asked them if they could get it ready for CRAN by the time I gave my talk, and they came very, very close, so I really want to include it. This can do regression or classification, and it only has an XY interface, which also uses a special object, lgb.dataset. The X matrix can be either dense or sparse or a file on disk. Categorical inputs can be either dummies or numeric encoding, which is pretty cool. If it's a binary outcome, it must be stored as 0, 1. This handles missing values for us, it can handle imbalanced data, and it can be trained on a CPU or GPU. So we go to our recipe, we make sure all the categoricals are stored as integers, and then we keep track of which of the inputs are categorical. Because when we create this lgb.dataset, we pass it our matrix for X, our matrix for Y, then we tell it which columns in X are categorical, even though they're stored as 0, 1, 2, 3 as integers. We then fit the model with LightGBM. We pass it the dataset, the n rounds with 100 in this case. The objective is binary, and we're going to evaluate it every 10 rounds. Even though our dataset was already balanced, I just want to show is unbalanced equals true will handle balance for us. There is no plotting method, so this returns an error. And we can calculate the variable importance using built-in functions, and this is the percent gain in accuracy. There are a lot more tuning parameters than I am showing, but num iterations for the number of boosting rounds, the learning rate, and the max depth are going to be the most important, and bagging and feature fraction controls how much randomness it gets. And you can even set different types of boosting. There are other models that we didn't have time to discuss. Rule fit fits a boosted tree, then extracts the rules and takes them and the original predictors and puts them into a penalized regression. Cat boost handles categorical variables similarly to GBM and is put up by Yandex. BART is a Bayesian boosted tree, and TensorFlow can fit boosted trees as well. There are so many different interfaces. We need to think about whether we use a formula or matrices, and then are they dense or sparse, or do we use a data frame or proprietary formats? How do we handle categorical variables, dummies versus numeric encoding versus factors? rpart uses a formula, C5 uses a formula or dense matrices. randomForest can use a formula or dense matrix, but you got to worry about the outcome variable. Ranger can also do a formula or dense matrix. GBM prefers a formula. xgboost and lightGBM need their own special objects. rpart can take categorical variables as a character or factor. C5 can also do the same, or dummy variables. randomForest can take factors or dummy variables. Rangers can take factors or dummy variables or characters. GBM can only take factors or dummy variables. xgboost prefers dummy variables, needs dummy variables. And lightGBM can take either dummies or numeric encoding. There's a lot to consider. We really need one standard. Caret used to be my go-to package, but not anymore. Now I use something tidy. Tidy models, also written by the author of Caret. We start with parsnip in order to specify the type of model. We say we want to fit a decision tree using rpart. Or we can fit a decision tree using C5. Or if we want to do a random forest, we can say we want to fit a random forest using the randomForest package. Or we could fit a random forest using the Ranger package. If we want to do boosted trees, we just say boost tree with the C5 package. Or boosted tree with the xgboost package. It's the same exact pattern for every type of model. Is the type of model you want to fit, then the engine. We are not doing lightGBM or GBM because they're not supported by parsnip. We then do feature engineering of recipes. But first, we split the data into training and testing like a good data scientist does. The pre-processing for rpart is just going to be upsampling, and then we will collapse some factor variables. Same with C5, we're just going to upsample. randomForest, we are going to upsample, make sure categorical variables are factors, and we're going to do imputation. Ranger is the same thing. C5 for boosting, we're just going to upsample. And xgboost, we are going to upsample, and we are going to convert our categorical variables into dummy variables. Then we use workflows to combine everything. Now I could have just loaded tidy models, but I like loading individual packages so I know where my functions come from. And for all the model types, it's the same. You take a workflow, and then you add in a recipe for the feature engineering, and then a model for the model specification. Here it is for the trees. For randomForest, it's exactly the same. A workflow, add a recipe, add a model. For boosted trees, it's a workflow, recipe, model. It's the same exact thing for all the steps. It's very common. It's very nice, easy to remember this. Then we can go ahead and fit the models. And it's the same for all of them. We take our workflow object and we fit it with the training data. So when you call fit, it does the pre-processing and then it trains the model. And that's the same for the trees, the randomForest, and the boosted trees. You fit the workflow with the training data. That's it. It's the same exact interface for all of them. So how do we do? I want to know our accuracy and our speed. So I put all of the workflows into a list so that I can iterate over them. We are going to use this in a little bit. We then define our quality metric, in this case, AUC. We then map over that list of workflows, and for each of them, we apply them to the data split object where we do the pre-processing and the training on the training data, and then we make predictions on the test data and see how we did with the quality metric. This code just mainly goes through and collects those metrics from each of the different models we fit, and then we plot the results. Here we can see that rpart and C5 did the worst. They're the simplest models. XGBoost, randomForest, and Ranger, the more complex models, did the best. But what good is a complex model if it takes forever to fit? So we're also interested in how long it took. So we use the bench package to fit each model repeatedly and see how fast they are. And now we see that the simple models, C5 and rpart, were the fastest, but XGBoost was right there with them. This complicated model was extremely fast, whereas the other complicated models, Ranger and randomForest, were the slowest. So what we really want to look at is the combination of time and AUC. We want to find the Pareto optimum. That upper left corner is where we want to be, and XGBoost is coming in at the nice combination of speed and accuracy. So what did we learn? There are so many interfaces to know. There are nuances for each model that we need to be aware of. And XGBoost is nearly the fastest and nearly the most correct for this data on my computer. And importantly, everything is easier with tidy models. Thank you.